So we are back after the break for our second tutorial. We talked about SAT solving before. Now we're going to talk about pseudo-Boolean solving, conflict-driven pseudo-Boolean solving. So we're trying to do the same thing as in conflict-driven close learning, CDCL, but in a pseudo-Boolean setting. And that raises the immediate question, what did you just say, pseudo-Boolean? Except that it's a cool name, I think. I mean, I think it's a very well-chosen terminology. Like, who wouldn't like to have a good pseudo-Boolean solver? That has to be something cool. But what is it? It turns out that this is actually well-established terminology from the 1960s. A pseudo-Boolean function is a function from Boolean values to the reals, or as a theoretician would say, it's a function from the Boolean hypercube to the reals. Like a Boolean function would be a function from the Boolean hypercube to 0, 1, but if you instead have general real values, then it's a pseudo-Boolean function. And it's well studied in operations research. 0, 1 integer linear programming would be a special case of this. And any pseudo-Boolean function over n variables can always be written as a polynomial of total degree at most n. This is not so hard to see. But we are going to be more restricted. We're going to insist on degree 1. Okay, we're going to insist on linear functions. And still, this will be, as we'll see, this is a fairly expressive setting. Why do we care about this? Why aren't we happy with CNF? Well, CNF is kind of cumbersome. If you want to say that the sum of 6 variables is at least 3, then, there's this cardinality constraint as a single line. And if you want to write it as in clausal form, either you're going to get some beast like this, or you have to use some kind of sophisticated encoding with additional auxiliary variables or something. And that's not so nice. Also, as we will see, if you reason with your pseudo-Boolean inequalities instead of clauses, then it's easy to build exponentially more powerful methods of reasoning. And yet, these 0, 1 integer linear inequalities, these pseudo-Boolean inequalities that we'll operate on, are close enough to clauses. We're in a setting that is close enough to SAT that it's sort of not too hard to see that we should be able to take good SAT techniques and port them to this new setting. And another thing, if we're looking at 0, 1 integer linear inequalities, is that there's potential for synergies with all the work that has been done in 0, 1 integer linear programming or mixed integer programming more in general. Okay, so what we're going to talk about now is basically in this tutorial, we want to take SAT solving and lift it to 0, 1 integer linear inequalities. This is our plan, except we're going to call it, a pseudo-Boolean problem is a 0, 1 integer linear program when a SAT person is talking about it. So we're going to consistently talk about pseudo-Boolean problems. And we'll set up some preliminary, some notation. And then we'll revisit conflict-driven search and learning again. Take another look at what we did in SAT and think about what it means to do, quote unquote, the same in a 0, 1 integer linear setting. And then we're towards the end of the talk, we're going to talk a little bit about possible open problems. Okay, so from now on, like whenever I say a pseudo-Boolean constraint, that's just a 0, 1 integer linear constraint. So we have a sum of an integer sum of literals that are variables or negated variables. And again, overline is negation. And the variables take values 0, false, or 1, true. And we can compare them with, less than or equal, greater than or equal, or equality, or strict inequalities, except we won't do that. We'll insist on something that's called normalized form. where all the constraints from now on, so from now on, actually, unless stated otherwise, for me, a pseudo-Boolean constraint will be a greater than or equal inequality, where all the coefficients are non-negative, and the constant term on the right-hand side is also non-negative and is referred to as the degree of falsity. And the reason I can do this is, again, because I have a sum over not variables, but over literals. So if a variable somehow contributes negatively, then I will just take the negated literal instead. Okay. So in particular, it's not so hard to see that the disjunctive clauses that we have in a conjunctive normal form formula are just pseudo-Boolean constraints in this way. A clause is just the sum of the literals, greater or equal 1. We saw a cardinality constraint, but then you can have also like completely general constraints like, I don't know, x1 plus 2 not x2 plus 3x3 plus 4 not x4 plus 5x5 greater or equal 7. Okay? This is a when I say, oh, this is a general pseudo-Boolean constraint, this is something like this. And again, you see, we always have normalized form. And this is mostly, normalized form is without loss of generality. And I mostly use it for convenience. I won't stress this, but just to see how this works, I mean, suppose you instead have an inequality that says minus x1 plus 2x2 minus 3x3 plus 4x4 minus 5x5, that this should be strictly negative. How would we turn it into normalized form? Well, first, we don't want strict inequalities, so we change to a less than or equal. Then we multiply by minus 1 to get a greater than or equal. And then whenever we have a literal L with the wrong sign, we just negate it and switch the sign, okay? Where we use that minus L is exactly the same as minus parenthesis 1 minus not L end parenthesis. So then we recover our general pseudo-Boolean constraint from before. And then one piece of syntactic sugar that I will use sometimes. I will sometimes write equality, but it's clear that that just means two inequalities greater equal or and less equal. And then I sort of implicitly normalize whenever I want. Okay? So I won't emphasize this whenever, but whenever it makes a difference, sort of we'll just implicitly think about things as being normalized. So yeah, so with this type of syntactic sugar that I already mentioned. One thing that I should maybe stress is if you want to write a less than or equal constraint, so some AI li less equal a, the way to normalize it is look at the total weight of the coefficients W. A less equal constraint is just you sum up with the same coefficients but negated literals, and then you just take the total weight minus a instead. It's sort of something that you get used to after a while. And since there are lots of equalities all over the place, whenever I put a dot over my equality, then this is when I want to stress something like that. C is syntactically this inequality, because we will also have equalities sometimes in the constraints. So I'm just trying to set up notation, like nothing strange is happening. As before, you should interrupt me at any point if you have any questions. Another piece of notation that is convenient is if I have two constraints C1 and C2, I will allow myself to add them and multiply them by a positive integer with the obvious meaning. And sometimes if I have a linear form and a constraint, I can also sum them up. Okay, so again, I hope this is sort of nothing, just making sure that when I write things like this, that I can add two constraints or that I can add a constraint in a linear form or multiply them. And again, obviously, when I add these two constraints, there might be cancellations and stuff happening, and I'm sort of just assuming that, well, we take these things, we sum them up, and then we cancel as needed and shift all the constant terms over to the right-hand side, and we normalize and things like this. This just all happens behind the scenes for us, whenever it matters. Another piece of notation, if I want to negate the constraint, C is again, canonical constraint C tends to be some AI Li greater or equal A, and the total coefficient weight is W. The negation of C is saying that this sum is strictly smaller than A, or saying sum of AI, not Li, greater or equal W minus A plus 1. Okay, the way to see that this is a negation is just think about it. Here we're summing up the non-contributions. Like if this constraint were to be true, then the contributions should be at least A. Here I'm summing up over negated literals. I'm summing up the non-contributions. And the non-contributions are actually summing up to W minus A plus 1. So the remaining contributions are then obviously at most A minus 1, which means that this constraint is violated. Okay. And one nice thing with pseudo-Boolean constraints compared to clauses is that I can take this negation and get a constraint of the same form. Like if you negate a clause, then you get a bunch of clauses. But here, the negation of a pseudo-Boolean constraint is just another pseudo-Boolean constraint. Some other thing, another very convenient piece of notation that we're going to use, I'm going to write things like Z implies the constraint C, or the constraint C implies Z, or maybe that Z and the constraint C are equivalent, they're the same. Okay. And it's important to note that these are also, here you have syntactic sugar, but I can actually write pseudo-Boolean constraints that mean exactly this. Okay, and this is, again, something that is not true for clauses, but it's true for pseudo-Boolean constraints. For instance, if I want to say that Z implies the constraint C, which is this guy over here, then I can take the degree of falsity A. I take A times Z bar plus the constraint. Okay, and it's kind of clear that if Z is false, then the implication doesn't say anything, and then A times not Z picks up everything we need, and we're off the hook. But if Z is true, then this part vanishes, and indeed the constraint has to hold. Right? In the other direction, it gets a little bit complicated, but maybe the easiest way to see that C implies Z is this beast is, well, this should be the same as not Z implying not C, and you will recognize that this part of the constraint, some AI, not Li, greater or equal W minus A plus 1. Remember, this is actually just the negation of C. Okay, I always have to think a little bit when I write this down, but I hope I got this right on the slides. And whenever I write Z equivalent to C for a constraint C, I will just think of this as these two constraints. Okay, and just to convince ourselves that whenever it's convenient, we can use this notation, and it kind of means what we expect it to mean. But these are, again, pseudo-Boolean constraints. And this is called reification. Z is the reification variable because it's true if and only if the constraint that it reifies is true. And just to see that all of these pieces of notation that we have behave nicely, what happens if I take C and sum it up with the negation of C? I get contradiction 0 greater or equal 1, which sort of tells me, I guess, that C and not C are not often true at the same time. From these definitions, it's clear, as I just said, that C implying Z is the same as not Z implying not C. And then you can say, okay, what if I have the reification Z implies C, and I know that Z is true? So this is like a unit constraint, if you wish, Z greater or equal 1. Well, I can just multiply it by the degree of falsity A and sum them up, and then I will recover C. So this says that if I know that Z implies C, and I know that Z is true, then there's a very simple syntactic manipulation that allows me to recover C. And conversely, if I know that C is true, and I know that C implies Z, and I just add up these constraints, then I get that Z is true, except I multiply it by this some kind of positive coefficient. Okay. These are the kind of things. It won't be important, but like the moral of this story is that, you know, these are just pieces of syntactic sugar, but it behaves nicely. So we can relax. Of course, we need to be a little bit careful, but like things will behave in a nice way. This is not important. Like if this seems like a mystery, then don't worry too much, because we're not going to use it heavily at all. I'm just flashing it because for completeness. Okay, one other thing that I just want to mention, like, what if you think that linear constraints is a big restriction? Well, it's not so hard to see that you can easily linearize. Like if I have a general polynomial constraint, some AI mi, greater or equal A for some higher degree monomials, products of literals, then one thing I can do, I can just take every monomial and reify it here. So these are the two constraints saying that yi is equivalent to all of these literals being true, which means that the monomial is 1. Okay, and once I have reified every monomial mi with a fresh variable yi, I just write a linear constraint saying that some ai yi greater or equal a, which is exactly the same as before. I'm not saying that this is a terribly good thing from an algorithmic point of view, but basically you could do it. So in fact, it's like, if you really want to, any pseudo-Boolean problem, you can linearize it and then write it as a 0-1 integer linear inequality in this way. So our formalism is not that restricted. Are we happy so far? But yeah, I won't talk so much about like we won't linearize going forward. We'll just think of the problems being linear. Okay, so now some pieces of terminology. What is a pseudo-Boolean formula? A pseudo-Boolean formula is just a conjunction of pseudo-Boolean constraints. Pseudo-Boolean solving, the pseudo-Boolean solving problem is given a pseudo-Boolean formula, is it satisfiable or is it feasible? Okay? Is there a 0-1 assignment that satisfies all inequalities? In a pseudo-Boolean optimization problem, we want to, in addition, among all satisfying assignments, find the one that minimizes some objective, which I will again write as sum over I, wi, li. I think of the w's as being positive, so it's like a normalized objective, if you wish. And this I can do because I have literals. And let's just agree that we always want to minimize. So to keep so that we don't have to worry about the objective. If you really wanted to maximize, well, then just negate the objective and normalize, and it's the same thing. Okay. So a pseudo-Boolean optimization problem is the problem of minimizing a linear objective subject to the constraints in a pseudo-Boolean formula. Okay. And now what we're going to talk about is pseudo-Boolean solving. It's not going to be hard, if you think about it, to extend what we do to sort of a vanilla pseudo-Boolean optimization algorithm. But basically, you can always just solve, and then when you found a solution with a particular value, you could just always add a constraint saying, now I want a value that is strictly better. This will be another pseudo-Boolean constraint, so I can add it to my formula, and I can resolve for as long as the formula is satisfiable. And then when it turns unsatisfiable, I know my best solution, my last solution was the best one. But there are, if you want to do optimization, there are better things you can do. We'll talk about that after lunch. So this is what we talk about for now. Pseudo-Boolean solving. Just to say that, to stress that this is actually an expressive paradigm. Suppose I have a graph with vertices v and edges c, and I have some kind of weight function on the vertices, say, then to encode the weighted maximum clique problem is I just say, well, if uv is not an edge, then at least I cannot pick both u and v to be in my clique. And subject to these constraints, I want to maximize the sum of the weights, that is, minimize the negation of the sum of the weights. Okay. Or if you want a vertex cover, you minimize the weight of the chosen vertices, where a vertex cover means that for every edge, I have to pick at least one of the vertices incident to that edge. Okay. Another problem that we're going to talk more about after lunch is, suppose I have a set of a collection of sets over some universe. And again, we have some weight function on all elements in the universe. And the weighted minimum hitting set problem is trying to find a subset of the universe which hits all the sets. So H is a hitting set if it has a non-empty intersection with all the subsets in my collection. But the sum of all the elements in H should be minimal. Okay, that's the weighted minimum hitting set problem. And again, this is just minimizing the sum of the chosen elements, subject to that in every subset there has to be a chosen element. And it's worth noting, actually, for all of these problems, that not only are they pseudo-Boolean problems, but actually, if you look at the constraints, they are actually CNF formulas. So we're just trying to optimize a linear function subject to a CNF formula. As we will see after lunch, this is actually the same thing as a general MaxSAT problem. So this serves to, if you think about like many problems of your favorite NP problems can probably be cast in this form. So this is a fairly expressive paradigm, and I guess I'm trying to say, you know, if we could find a good algorithm for problems like this will probably be useful. Okay. So that's what we're going to talk about. This tutorial is about pseudo-Boolean solving, the decision problem. And then we'll go on to talk about MaxSAT solving, or more general optimization problems. And we'll talk about also a little bit about mixed integer linear programming. And a little bit of a spoiler alert, we'll see this more, I think, in particular in the final lecture. But if you look at what people do in SAT solving and pseudo-Boolean solving on the one hand, and in mixed integer programming on the other hand, sort of what a SAT solver and a pseudo-Boolean solver do, they always work, they have partial solutions, Boolean solutions, and try to extend them to full solutions. But then when they hit conflicts, they try to see, okay, this didn't quite work, and then you back off. But you're always like, you have a partial valid solution that you're trying to extend. A MIP solver kind of does the opposite. It just relaxes the whole problem and says, screw the integer constraints. Let me just find over the rails the best solution I can. And then you find that solution and you say, oops, that wasn't integral, too bad. And then you try to fix it to say, well, can I find an integral solution somewhere nearby? Okay, and these are kind of two fairly different I mean, we're still, both of them are shooting for a 0-1 solution in the end, or an integer solution in the end, but sort of they're coming at it from very different directions. And another difference is also, which we already talked about in the tutorial on SAT solving, how you deal with the trade-off between inference power and inference speed, where I would say that SAT solvers pretty much prioritize speed above everything else. As we saw, for instance, decisions are made extremely quickly. And also other parts of the inference. Whereas when you're doing mixed integer programming, a decision is something that you think about very, very carefully. This is a major thing for you. Just, you know, picking the VSIT score, that would be very irresponsible. We'll talk more about this later. Okay, so now with a view that towards, we want to generalize SAT solving to 0-1 integer linear programs. Let's recap what we had again. We talked in the previous lecture about the DPLL method, which was basically just backtracking, assign values to variables in hopefully smart ways, and backtrack when you violate a constraint, when you hit the conflict. And what conflict-driven clause running added on top of this was you're analyzing the conflicts in more detail, adding new clauses. And we saw that not only did you backtrack one level, you could also backjump several levels that we saw. And you could also use the conflict analysis to guide other heuristics. For instance, collect these VSIT scores that told me what were interesting variables to branch on. And we're going to focus again on how to assign variables and analyze conflicts, which means that we have this again. This is the final time you're going to see this slide, but basically what CDCL does is if you have a conflict, you analyze it. Otherwise, if you can propagate, try to propagate. Otherwise, check if you should restart and clear your partial assignment, your tray. If not, you check if it's time to throw away roughly half of your clauses. And otherwise, make a next branching decision. We're going to focus on this conflict analysis part and see how to extend it. I want to stress that how to make decisions, how to reduce your clause database size. These are also very, very important aspects. They are not so well understood for pseudo-Boolean solvers, and I won't talk about them, but that doesn't mean that they're not important. And again, recapping what we saw before, the conflict analysis was, while we started with the learned clause being the conflict clause, while it didn't look nice to us, while it wasn't a unique implication point clause, we looked at the latest propagation that the conflict side constraint didn't like. We saw the reason constraint for that propagation, and we resolved the two, and then we kept going doing this derivation until we saw a constraint that we liked, and then we decided to learn it. Okay? This is what we want to do, and we just want to keep this pretty much, but do it for 0-1 integer linear inequalities. And the only problem is we need to figure out what this means. Okay? What have people tried? Well, one thing that you can do is you can just keep your pseudo-Boolean formula, but then propagate on these constraints, but then basically learn clauses by conflict-driven clause learning conflict analysis. Another thing that you can try to do is you can take your 0-1 integer linear program, you can translate it to CNF in some clever way, better than what I showed you on the initial slides, because that causes an exponential blow up. So there is a whole literature on how to translate pseudo-Boolean constraints to CNF. Pick some really, really smart translation, maybe in an adaptive fashion, and then run a CDCL solver. Okay? This is not what, these are all good approaches, interesting approaches. They're not why we're here today. What we are going to talk about, what I'm mainly interested in, is keeping the input as it is. We keep the pseudo-Boolean constraints, we keep the 0-1 integer linear inequalities, and we want to somehow do conflict analysis on them natively. In particular, this was first pioneered, and we're going to focus on the method that appeared in the solver Galena by Chan-Kuhlmann, and that is today supported in SAT4J and rounding SAT and other solvers building on these tools. Okay, again, what does it mean to do the same thing as SAT-based conflict-driven solving? Well, for the assignments, we had the idea that as long as we can propagate, let's propagate. And then when we can no longer propagate, we'll make a branching decision. And then at the conflict, well, we already saw the conflict analysis algorithm. We want to run some kind of conflict analysis to derive a new 0-1 integer linear inequality. And then once we have this, we're going to back jump. And then hopefully we're going to see a new propagation, just as we do when we learn clauses. And then we're going to switch back to searching. That's the plan. Okay. And the only thing is now, like, what do we need to figure out? Well, we need to figure out what does it mean to propagate, how to detect propagation, and what would it mean to do conflict analysis. But that's the plan, okay? Excellent. Again, I'm going to use rho to denote a partial truth value assignment. And since we're doing solving, I think of this partial truth value assignment with some structure. It has a chronological order. And I know for every assignment in rho that it's either a decision, it's a branching decision, or it's a propagation. And then I know what the reason constraint for this is. Okay? Just as in SAT solving. How do I know if something propagates? Well, a clause propagated when it said, listen, if you don't set this clause to precisely this value, then I'm going to be very unhappy and there's no way you can make me happy again. Okay, so propagation should mean exactly this. Like a pseudo-Boolean constraint propagates a variable x to true if it is the case that if x is set to false, then there's no way of making this constraint happen. Okay. Well, how do you measure happiness? Well, you typically call it not happiness, but slack. So the slack of a constraint, that is sum of AI, Li greater equal A, as always, given a partial assignment rho, is the following. You look at all the literals that are not falsified. Okay? The falsified literals, we know they're not going to contribute. Note that I'm assuming normalized form here. This is important, right? Everything is non-negative. So like if Li is set to true, this contributes AI meaningfully. If Li is false, then it's not contributing. Okay? Everything you see here is non-negative. So falsified literals Li, they cannot make the constraint happy. Satisfied literals definitely help to make the constraint happy. Unassigned literals could still make the constraint happy. So let's sum up everything that could potentially help or does already help. Let's sum up all of these AI, and let's subtract what we need, capital A. That's the slack. That's how much margin of error we have. Does this make sense? So basically, and in particular, it's clear that if this slack is negative, then constraint C is violated. There's no way to extend what we have now to a total assignment that satisfies C, because there's not enough contributions left. This clear? This is kind of an important point. So let's just do a small example. So here is our favorite constraint from before. Here we have some partial assignments. Under the empty assignment, we just sum up everything. We get a total weight of 15 minus 7, that's 8. So the slack is 8, quite a lot of margin. Okay? Suppose now that we assigned x5 to false. So I represent the partial truth value assignment as just the literal set to true. Okay? So now x5 is false. Then x5 no longer contributes to the slack, and so this potential contributions of the other guys is 10 minus 7, that's 3. Okay, and now note the following. 3 is strictly smaller than the coefficient of not x4. If I would now set x4 to true, then I lose another potential contribution of 4, then my slack would go negative. Okay, so if I have a literal with a coefficient that is strictly larger than the current slack, I'm not allowed to screw up this literal. So this is what it means to propagate. So in this case, under not x5 being true, under x5 being false, this constraint propagates x4 being false. Okay? And now suppose that the solver goes off and does some other things. It sets x3 to false, x2 to true. Now when you sum up the contributions, x1 could contribute, it's unassigned. x2 does not contribute, x3 does not contribute, x4 does contribute, x5 does not contribute. So we have potential contributions of 5, but we need 7, so the slack is minus 2. So we have a conflict. And note, interestingly, in contrast to clauses, there are still variables that are not assigned. Like nobody has decided on x5, but it doesn't matter. We already know that this constraint is violated. For a clause, you never know until you've assigned all the variables, but for this kind of constraint, although it doesn't matter whether we set x5 to true, it won't be enough. Okay, so now I claim we know what it means to propagate. Like a conflict is negative slack, propagation is current slack is strictly smaller than the coefficient of this literal. Does it make sense? Okay, another question is, algorithmically, how do I detect unit propagation? Excellent question, challenging problem, research needed. Okay, but this is harder than in CDCL. I didn't tell you how CDCL propagation works, and I think we should focus on other things, but it's pseudo-Boolean unit propagation. There are good algorithms, but there's certainly room for improvements. And given that you remember from the SAT solving lecture that we had that 99% of all decisions, you would expect them to be propagations, it's kind of clear that efficient propagation would be really nice. Again, this is an important algorithmic question, room for work. Okay. Now, what would it mean to do conflict analysis? Let's look at, here was our CDCL example again, our first conflict. What did we actually do during the conflict analysis? Okay. So I claim that what we did, we derived clauses, and where we maintained the invariant that the clause we had on the conflict side, I'm going to say that this is sort of, we start with the conflict on the conflict side, and then I think of all the derived clauses as being on the conflict side until we finally learn a clause. it was always the case that I sort of derived new clauses and I removed literals from the trail one by one, but the shrinking partial truth value assignment always violated the conflict side clause that I had derived. Okay, notice that first I started with this whole trail that violated the conflict clause. Then I removed Z and got I removed Z, but then the trail violates this guy, and then I removed Y, and the trail still violates this guy. So this means that at all times, these constraints are explaining that, already I have removed some assignments now, but already the assignments you made were hopelessly wrong because of this. Okay. So as I'm doing my conflict analysis, I'm maintaining the invariant that the derived constraint is explaining why the assignment up to this point is a non-starter. Okay. Which means that adding the currently derived constraint to my database of constraints would have told the solver something that it didn't know, because if it had this constraint in the database, it would already have terminated. Okay? And the only question now is, when do I stop this process? But I can stop it at any point because any constraint is an explanation of why I failed. Okay, is this making sense? This is like, and we're going to say, I like this invariant because this is sort of a nice, easy invariant, easy to understand. I want to maintain, as I'm doing my conflict analysis and trimming, removing assignments from the trail, making it smaller and smaller, I want to maintain the invariant that the constraint, the current constraint, is violated by my current partial assignment. Because that means that at any point I just stop and I know that I'm not going to make that assignment again because that would violate this constraint that I had derived. Okay, I'm belaboring this point a little bit, but that's because it's important. And I terminate when the explanation looks nice. What does nice mean? It means that the constraint is asserting, or it's a unique implication point constraint, which means that when I back jump, this new constraint that I've learned immediately gives me a new propagation, flipping some previously assigned literal. Okay. Okay, so now we just need to do this, and we did the conflict analysis using resolution, and clearly we can mimic resolution. If I have a resolution step with the clauses X or not Y or Z and not Y or not Z and resolve them, I can just take the corresponding pseudo-Boolean constraints and add them up, and sure enough, here Z will cancel and leave a 1. And so adding up these two constraints, it's X plus 2Y bar greater equal 1. And this goes back to the around 1990 in work by Hooker, who called it generalized resolution. So basically, for any two, suppose I have one constraint containing x1 positively with coefficient a1, another constraint containing xy negatively with coefficient b. Basically, I just compute the least common multiple of a and b, and I multiply this constraint by c divided by a1. I multiply this constraint by c divided by c divided by b1 here, c divided by a1 here, and then I just add them up. And if I do this, x1 will cancel, and this is kind of what resolution does. Sorry for screwing this up. Was this kind of clear? Just take the LCM, multiply this one by c divided by a1, multiply this by c divided by b1, then clearly the coefficient here after this will be c on both sides. So when I add them up, x1 will just vanish. So far, so good. This looks a little bit like resolution to me. We're kind of resolving 0-1 interlinear inequalities. Okay, this is making us happy. We see lots of nodes. We're making progress. Except that that too is kind of a little bit annoying, right? The clause would have been x plus y bar greater equal 1, not x plus 2y bar. So let's add. But since since we are only interested in integer solutions, actually 0, 1 solutions, clearly the only way x plus 2y bar greater or equal 1 can hold is that x plus y bar greater or equal 1 holds. This is like a logic consequence. So let's introduce a rule for this as well that says basically, well, again, assuming normalized form, importantly, everything is non-negative. If I have a constraint sum of ai li greater or equal capital A, I can always just trim all coefficients to be at most capital A, and it will be logically like equivalent. You happy with this? Okay. And the important rule is to see that this is a rule that is sound over the integers, but not over the reals. This is good news because we're trying to do SAT solving. So we should have a rule. I mean, just summing up, if you look at the generalized resolution rule, the way we defined it, this is sound over the reals. Okay, so we're not going to solve a Boolean problem with this rule only. We need something like saturation. Okay, fantastic. So, and in fact, I'm sort of misrepresenting what Hooker did. I mean, he, of course, realized this. So his generalized resolution rule kind of did this already. But for us, as we'll see, we want to sort of distinguish the canceling part from the saturation part. Okay, so we're ready to do conflict analysis now. Here we have two constraints, C1, 2x1 plus 2x2 plus 2x3 plus x4 greater or equal 4. And another constraint, 2x1 bar plus 2x2 bar plus 2x3 bar greater or equal 3. And if you look at this, I'm sort of obfuscating a little bit, but constraint number 1 says that the majority of x1, x2, x3 are true. And constraint number 2 says that the majority of them are false. So clearly this should not end well. Any good solver should be able to derive contradiction from this. Let's see what happens. Our solver starts by setting x1 to false, because why not? And now you realize that once you set x1 to false, constraint C1, you do the slack calculation. First, the slack of C1 is like, what is it? 7 minus 4, that's 3. But then when you set x1 to false, the slack goes down from 3 to 1. And that actually triggers propagations for both x2 and x3. This is another kind of interesting thing if you're coming from a SAT point of view, that the same constraint can fire several times. Like a clause only propagates one variable and then you're done. In general, the pseudo-Boolean constraint can propagate multiple variables at the same time or even at different times. Okay. Now, once we have this propagation, x2 and x3 are both true, let's look at the slack of C2. The slack of C2 is 2 plus 0 plus 0 minus 3, that's minus 1. We have a conflict. Time to do conflict analysis. Are we fine so far? Okay. And it's clear what we should do. We pick out the reason. The reason is C1, and we should resolve it with the conflict C2 over the propagated variable x3, because this is what conflict analysis did. And we're in luck because x3 appears with the same coefficient, so we don't need to do any least common multiple thingies computations. We just add these up. And when the dust settles, we derive x4 greater or equal 1. This is the first step of our conflict analysis. Are we happy with this? What is our invariant that we want to maintain? Well, basically, we have the assignment x1 true, x2, x3 false. We're going to resolve, we're going to trim x3, and we want the constraint that is violated by the rest of the assignment. Okay, but x4, but whatever is the reason for this conflict, it's not x4 because x4 hasn't even been assigned. Okay, you could say, yeah, but I mean, we're learning something about x4. It's true, and it's true that we're learning that it's true, and it's kind of an interesting fact, maybe. But it's very clearly not why we ran into this conflict. Okay, so we lost the invariant that the conflict side constraint is conflicting. And again, why are we so unhappy about this now? We're like really unhappy. Well, we're unhappy because our conflict constraint, the constraint that we're learning should explain why the assignment we did was wrong. But again, x4 greater or equal than 1 is maybe an interesting statement, but it doesn't explain anything what we did wrong so far, because we didn't even touch this variable. Okay. What happened? Why did things go wrong? Well, if you think about it, we were trying to get the constraint that is violated over just x1 being false, x2 being true. And look at C1 and C2. What do they think about this partial assignment? Well, they're actually pretty happy with this assignment, because C1 says, well, x4 could still contribute 1. And if you can give me x3 like at least a half, then I'm willing to settle. And C2 can say, I hear what you're saying, a half, yeah, we can agree at the half, because if I can get at most a half of x3, then I'm also happy. Okay? And then when you resolve them, this is just, again, this operation is sound over the reals. So if you take two constraints that are actually happy and add them up, then the sum is going to be happy also. So we lose the conflict. Why did we lose the conflict? Because the propagation wasn't tight enough. Because these constraints just wanted x3 to propagate to a half, and what we did, we said, okay, we're propagating to a half. Well, there is no value such as a half because we're Boolean, but our derivation rules did not know this. Okay. So somehow what we'd like to do is to strengthen the propagation to be actually tight, to propagate x3 to 1 also over the reals, which if you think about it would mean that a tightly propagating constraint is a constraint that has slack 0. So I would like a reason C with which over row prime x1 being false, x2 being true, has slack exactly 0. And the problem is I don't have such a reason. How can I get one? Well, I claim that one thing we can do is we can apply weakening, take some literal Lj that appears in my constraint, and just remove it, and look at what we have left. We say the sum over the other constraints must contribute at least A minus the coefficient of the guy we removed. So we're going to do this, and then we're going to saturate, and then we're going to try again. And this is essentially what Chai-Coleman did in Galeno. Okay, let's see what happens. Try to do this. So we want to weaken on a non-falsified literal, but not on the propagated one, because then we can't resolve. And then we saturate, and then we resolve. Okay. So here is our reason C1. Again, let's weaken on x2. Then we get the sum here is greater or equal to. Then we saturate. Nothing happens, unfortunately. And we resolve. And now we get 2x2 bar plus x4 greater or equal 1. It actually got worse than before. Okay, I would argue. Not so great. In particular, we still have a non-negative slack. Okay, but we're not giving up that easily, so we're weakening even more. I mean, we can't weaken on x1 because it's falsified. So weakening on it would introduce a contribution that is not there. But we can weaken, and we can't weaken on x3 because then we lose the variable we want to resolve over. But we can weaken on both x2 and x4. And if we do that, we get that, well, x1 plus x3, summing them up with coefficient 2 is at least 1. And now something happens when we do saturation, right? Because now we decrease these coefficients from 2 to 1. And now we resolve. How do we resolve? Well, we resolve over x3, which has coefficient 2. So we should multiply this whole thing by 2, and then we sum up and add. And we get 2x2 bar greater or equal 1. Question, are we now happy? The answer is yes, we're happy. Because this shows that indeed, we're looking at the assignment setting x1 to false and x2 to true. And this constraint said, that's a terrible mistake. What did you just do to x2? You shouldn't have done that. Okay, so this means that now we can continue our conflict analysis, or we could even say, well, this is a unit constraint. We can just learn this and backjump. We've actually learned unconditionally now that the only way to satisfy these two constraints, if there is a satisfying assignment, which we don't yet know, but the only way of satisfying these two constraints is to set x2 to false. This is now with unconditional derived this. Okay, this is a very, very important point. Are we making sense here? Okay, the only question is why is this working? Maybe. Yeah, so again, we can learn this concept. We probably want to saturate it also. I mean, we can bring the coefficient down to 1, and then we can back jump. And now if you think about it, by symmetry, what we have before, we now know that if we just back jump, x2 is false. Well, by symmetry, that will give us the same trail again. If x2 is false, then c1 is going to propagate x1 and x3 to true, and then c2 is going to be unhappy again, and we get a conflict without any decisions. And that means if a pseudo-Boolean solver detects conflict without any decisions, we know it unsat. So just learning this constraint, back jumping, propagating will lead to contradiction. We're done. Okay, or we can sort of do this conflict analysis step if we also want it, but it won't be needed. Okay. So just learning this constraint, back jumping and propagating will tell the pseudo-Boolean solver that we have a contradiction. What did we do? Well, we took the reason side constraint and we changed it. We weakened it and saturated it. We said, let's try to resolve the current reason with the learn constraint over the propagating literal and check the slack. As long as the slack is non-negative, which we don't want, find a literal, which is not the propagated one, which is not falsified, weaken on it, and saturate and update the reason to be this, and try again. Okay. And do this while the slack is non-negative, and then return the reason. Okay, this is what we did, and the question is, will this work? And I claim it will always work. It's guaranteed to work, but why? I mean, it's not at all clear. I mean, potentially we could weaken away all weakenable literals and still have non-negative slack, right? In which case we just crash. But this doesn't happen. Why doesn't it happen? Two things. This is like it's a proof by intimidation almost. So two things I claim. I claim that slack is sub-additive. If I have two constraints C and D, I multiply C by lowercase c, D by lowercase d, and I sum up and get a new constraint. The slack of this guy is at most C times the slack of capital C plus lowercase d times the slack of capital D. It's not an equality, as you can think about, but it's less equal, so it's sub-additive. Huh? And the second thing is, we know in our conflict analysis, our invariant says that the conflict side constraint explains what went wrong, which is the same thing as saying it has negative slack already. When we weaken on the reason side, that never changes the slack because we're removing the maximal contribution. So it's like weakening before and after slack is exactly the same. And saturation, on the other hand, can decrease the slack. And if you just think about when the maximum number of literals have been weakened, and there's only one literal left that is not falsified, after saturation, that coefficient will have to be exactly the same as the degree of falsity on the other side, and the slack will be 0, which means that we have tight propagation. Okay. This sort of requires maybe 5 minutes offline, but this is, I mean, this is true, and this is why it works. Okay. So now we have our conflict analysis algorithm. Remember, I told you about CDCL conflict analysis. We have exactly the same algorithm. The only thing we changed is before resolving the we're not resolving the conflict side learn constraint with the reason. We first massage the reason with the so-called reduction algorithm, and then resolve the conflict side constraint with the reduced reason. Other than that, everything is exactly as before. So now we have our first pseudo-Boolean solving algorithm. Again, and I want to stress, the only thing is this mysterious reduction step applied on the reason side. And this is, in fact, to the best of my understanding, what the default setting in SAT4J does. Okay. How are we doing so far? Questions? Comments?
In which order you decide which variable you are going to weaken first? In say reduce stats, do you weaken all?
Excellent question.
Everything or?
Excellent question. No, I probably want to do it only one at a time. I could weaken all, but then that will kind of degenerate to more or less the CDCL. So I want to probably weaken one at a time. I should never weaken falsified literals. I could weaken satisfied literal or unassigned literals. I could weaken depending on coefficient size also. Like if I weaken on a smaller coefficient, that's sort of losing less information. But on the other hand, less things happen. How should I do this? Excellent question. I think we just don't know.
Okay, but the best way possible would be to weaken away the less number of variables possible?
Not even that is clear.
Okay.
I mean, in that will give you the strongest reason constraint. Will the strongest reason constraint give you the syntactically best conflict analysis? Not clear.
Okay.
And in general, probably the answer is no. I mean, this is, you're asking an excellent question, which could be a good topic for an afternoon discussion tomorrow or on Thursday. Like, we don't know, and I think we should figure out how to do this. Like, if we're going to do this kind of conflict analysis, clearly we need to understand how to weaken. And we don't. But we know that any type of weakening will work, but we don't know which one is the best one. Okay, so now we have a pseudo-Boolean solver, but we do have some problems that we talked about. It's harder to detect propagation. Suppose you have, sum over x1 up to xn greater or equal n minus 1. How can you, it's sort of clear that, again, for a clause, we didn't talk about this, but even if a clause is gigantic, as long as you know that there are two non-falsified literals in the clause, it's not propagating. Okay. But here it's kind of clear that you have to keep track of all variables to know that this constraint is not propagating, because as soon as a single variable goes to false, all of the other ones will propagate to true. Another problem is that when we're doing this generalized resolution steps, we're computing least common multiples, which can pick up a lot of, and if you imagine, like, that will pick up probably a factor of at least 2. And if you're now doing, a 100 steps and you're multiplying by 2 every time, you're basically going to run out of fixed integer precision pretty soon. And this, so SAT4J runs in arbitrary precision, but it does have a problem with that. If you're unlucky, integer coefficient sizes will just explode and your solver grinds to a halt for that reason. Okay. And one other thing that I don't have time to elaborate on is, if I give you a CNF input, this whole conflict analysis algorithm that I gave you will actually do nothing other than CDCL, but in a more expensive way. Okay, so we have a slower algorithm to do exactly what a CDCL solver would have done for us. So this is terrible for CNF input. Okay. So what can we do about this? So I talked during the first lecture about cutting planes. And the cutting planes proof system does not use saturation, but uses a so-called division rule. So you have still that all literals are non-negative. You can take positive linear combination of constraints. This is a combination of addition and multiplication. You can divide. I've written the division rule slightly differently here. I'm no longer assuming that C is a common factor. I can actually, if you think about it, I'm not going to elaborate this, but you can just divide by C everywhere and then round up everywhere, and it's still going to be fine. And this is actually what is known as a Huat-Algomori cut. So this is how cutting planes is defined in the theory literature. And we know that this way, this proof system is implicationally complete, meaning if I have a bunch of constraints that semantically implies some other constraint, then with these rules, I can derive this other constraint. Whereas if you use the saturation rule, it's not implicationally complete. Okay? So there are constraints that are implied, but that cannot be derived by cutting planes with saturation. So that raises the question of, well, you know, maybe if we use these rules, we can get a stronger conflict analysis. And in fact, it has been tried before for integer linear programming, but with not so much success in practice. But we're going to try it now for our setting. So again, we have the same two constraints. We have the same trail. We have a conflict. And now we're going to do the following. Again, so where did this come from? Well, we're going to look to weaken the recent constraint again on some non-falsified literals. But we're going to weaken only coefficients that are not divisible by the propagating literal coefficient. Okay, because we want to do division later. Okay. And then we're going to divide by the coefficient of the propagating literal, and then we're going to try to resolve. And we're going to try this over and over again and hope that it works. Okay, so let's see what happens. In this case, we don't have much choice. The only literal that is not falsified and is not divisible by 2, the coefficient divisible by 2, that's x4. Okay, so we weaken C1 on x4. And then we divide by 2, and we get x1 plus x2 plus x3 greater or equal to. And we should resolve this with the conflict constraint. So we multiply this by 2, and we add up. And we get 0 greater or equal to 1. In the first step in conflict analysis, we suddenly got, just like that, conflict analysis. Conflict, like 0 greater or equal to 1. And obviously, I set this problem up nicely, right? But this shows that, you know, already shows that something interesting can happen. So we cannot terminate the solver immediately. It actually, during conflict analysis, it suddenly, like out of the blue, derives contradiction, which is again something that would not, in SAT, this wouldn't happen. Like if you're somewhere in the middle of your search and you do conflict analysis, you never derive the empty clause, unless if you're at decision level 0. But here, it just happens out of the blue. So to say what we did, what did we do? Well, we have a recent constraint. We let C be the coefficient. And while we cannot resolve to get a negative slack, we picked some reason side literal, which is not the propagating literal, and which is such that the coefficient of this literal is not divisible by the coefficient of the propagating literal. We weaken, and then we again try to resolve the conflict side learned constraint with the reason side constraint divided by this coefficient. Okay. And again, I just claim that this is guaranteed to work. And again, we don't have too much time to go into details, but this will probably work if I will get a reason side constraint with slack 0. Again, because I know that slack is subadditive and I have negative slack on the conflict side. So then by subadditivity, if I take a 0 slack thing and add it up with a negative slack thing, I'll get negative slack. And again, the slack doesn't change after weakening. So it always holds for the reason side constraint that the slack is non-negative because we don't already have a conflict. And the slack is strictly smaller than C because L is propagating, right? L wouldn't be propagating if the slack was C or larger. So we know that the slack is strictly smaller than C. And now, when you've weakened away everything that is not divisible, in the final step, we will have weakened away everything non-falsified that is divisible. And that means that when you, the slack of C reason divided by C will be actually true division. There's no sort of rounding in the division. So that's why after maximum number of weakenings, we will have slack greater or equal to 0 still, but strictly less than C divided by C, which is 1. So the slack is 0. And again, I'm going fast, but this is guaranteed to work. Okay. And in, just to, this is getting a little bit technical, but rounding SAT is actually doing something slightly more aggressive, or the first version of rounding SAT did something more aggressive. It actually did, and related to Pierre's question, notice that the proof kind of assumes that I've weakened everything away and then says, well, at this point it will work. So you could actually just weaken everything away, and then you know at that point you have a slack 0 constraint. And this would be this algorithm. Just weaken away all the non-falsified literals with coefficients not divisible by the coefficient of the propagating literal, and divide, and that's my reduced reason. Okay. And actually, this very aggressive reduction method is also used at other places in rounding SAT in the 2018 version, although we've tried to dial this down a little bit in later versions. So there, by now, I think there are many versions floating around. And maybe, I don't know, Mark Vinyals here in the audience might be the person who knows best exactly what's happening in the current version. I don't know. This is a topic for an offline discussion. So I think what we had in 2018 was that we actually applied the reduction method to both the conflict side and the reason side constraints. And then when you're done and want to learn the constraint, we do a final reduction also, which is also related to Pierre's question. Note that every reduction step is sort of weakening the constraints, but it's also removing variables. And somehow empirically back then, we found that although this constraint is weaker when you round it, it's somehow more compact and more helpful. But we don't understand this very well. It just seems to work. Okay, what can we say about division versus saturation? We can say that the way our conflict analysis seems like, well, when pseudo-Boolean reasoning is not paying off anyway, then we were processing the conflicts faster in rounding SAT than compared to, for instance, SAT pro J. When pseudo-Boolean reasoning helps, our conflict analysis becomes slower, but it seems to pay off. And another very nice thing is that since we're dividing all the time, our integers will be much, much smaller, so much smaller that actually the default version of rounding SAT runs in fixed integer arithmetic, which is something that SAT for J could not possibly do. However, some problems that we really care about, such as arithmetic circuit verification problems, very embarrassingly, the saturation-based method in SAT for J is much better than the division-based method in rounding SAT. We still don't fully understand why. We still have the problem that propagation needs to be done efficiently. We still have the problem, if you look at the algorithm, that if I give you a CNF, I will still get only a very, very expensive version of CDCL conflict analysis. And another sort of weird thing is that sometimes we can cook up infeasible 0-1 integer linear programs that are even rationally infeasible. So the LP relaxations are infeasible, and the running SAT solver would just run forever. Okay, a single LP call would say, sorry, this is not a Boolean problem any longer, it's just infeasible. And running SAT runs forever. Okay, so a few more things before we wrap up. Some other rules that are relevant that we'll maybe talk about later. One thing, if we get a general constraint like this, 3x1 plus 2x2 plus x3 plus x4 greater or equal 4, say, if we don't like integer coefficients in general, you could always round this to a cardinality constraint by looking at the heaviest coefficients and say, how many of these do I at least need? From here, it's kind of clear that at least 2 of these variables have to be true, right? So I can actually derive this cardinality constraint. And in general, this is what the Chai-Kuhlmann solver did. They just sort of rounded to cardinality constraint and said that actually we don't need these general coefficients. Cardinality constraint is good enough. And here is basically what I just said. The cardinality constraint reduction rule is basically you pick the heaviest coefficients and you look at how many heavy coefficients do I need to reach the degree of falsity. And that's the cardinality constraint you round. But this is like the example. Is this more or less clear? And then, of course, it's not obvious that this would be like the best cardinality constraint. Sometimes you can also combine this with weakening. But if I have a pseudo-Boolean constraint like this, I can always round it to a cardinality. Another interesting rule that has appeared, I think, in the operations research community that we haven't used is, suppose I have these 3 constraints, x plus y greater equal 1, x plus z greater equal 1, y plus z greater equal 1. And I set x to 0 and propagate. Well, you look at these, you realize that actually these clauses say that at least 2 out of these 3 guys are true, right? And you realize that, well, either x is true, but if x is false, then x plus y is true. This is by propagation. X propagates to true, z propagates to true. So this constraint is actually over-satisfied by a margin of 1. So you realize that now if you add x to this, you say, well, either x is true, in which case this inequality definitely holds, or x is false, but then this is over-satisfied, so then this again holds. So by this type of strengthening, you can recover stronger constraints. So if setting L to false over-satisfies this constraint by an amount k, then basically you can add k to the degree of falsity if you also add k times L to the constraint. The problem is that, I mean, as we see, you can recover better encodings from CNFs here, but it seems hard to get this to work in practice.
Do we know how to simulate this with division, say?
Good question.
Okay.
I have a good question. This particular thing should clearly work. Good question. Yeah, I don't know. Another thing, suppose I have 2 constraints which are exactly the same, except that I have 2x on the left and 2x bar on the right. Then it's kind of clear that, well, x is either true or false, so the rest of the constraint has to hold, right? Okay, how can I derive this when I can resolve the 2 constraints, but that will give me something much, much, much weaker. I could try to saturate, it gets a little bit better. I can try to divide, that doesn't really help at all. Clearly, this constraint is much weaker than this. Okay, so it would be nice to have a rule which a former PhD student of mine, Stefan Gocht, called fusion resolution. Like if I know that A times L plus some sum greater or equal B, and L times not L plus the same sum greater or equal B prime, then I know that the sum Bi Li is at least the minimum of these 2 guys. And we do have some benchmarks where you have really short proofs if you add this rule. And if a solver could somehow maybe use this rule, this would be super intriguing, but we don't know how to do it in practice. And I think we also, it's another, like, could cutting planes do this? I don't know. Or maybe, I mean, we know of other things that are very similar to this that actually cutting planes cannot do efficiently. I don't know if we thought about exactly this. I don't think so. Okay, so again, what problems do we have? We have that the CNF input is very problematic. What could be done about this? Well, there are some papers that propose to detect cardinality constraints either as a pre-processing step or on the fly. It's not efficient enough in practice, at least not yet, but this is an interesting research problem. As I said, we sometimes have very poor performance of pseudo-Boolean solvers, even on rationally infeasible 0-1 linear programs. And we don't understand, there are no theory reasons for this, because if a linear program is infeasible, then that's very easy for cutting planes. We will talk about later today about how to maybe integrate pseudo-Boolean solving and linear programming to address this. Pre-processing is just a complete unknown area. Pre-processing is very important for SAT. Pre-solving, as it's called, is very important for mixed integer programming. We don't have it for pseudo-Boolean solving at all. One idea would be to take like a good MIP pre-solver and try to run it on a 0-1 integer linear program before. It seems a little bit tricky to get this to work, but it's again another interesting research problem. Making solver performance more robust would also be good. It seems anecdotally that CDCL solvers are more robust to things like if you permute the order of the constraints and so on. That doesn't affect CDCL solvers so much. It does affect pseudo-Boolean solvers more, it seems. Okay, more challenges. We already saw that we can use division or saturation for conflict analysis. Could we maybe use other rules? Should we try to adapt? Adaptively try to see during conflict analysis which kind of rule seems to work best. There's the concept of the SAT4J team discovered that sometimes you pick up irrelevant literals that are just not important. We saw this X4 was an example of an irrelevant literal in our first toy example. If we could have just detected this and removed it, then we would have had a better conflict analysis. We already talked about that conflict analysis in a pseudo-Boolean setting, there are much more degrees of freedom. How should you do the reduction? Do we want to learn only cardinality constraints as in Galena or more general pseudo-Boolean constraints? There are also other things. Sometimes you don't need to resolve at all because the slack is so negative that you could sort of just skip a step. Sometimes you can get a choice when you've learned an asserting constraint that it could be asserting at several levels. How far should you back jump? Should we go for arbitrary integer precision or fixed precision? None of these questions, to the best of my understanding, have been systematically investigated. In CDCL conflict analysis, an important post-processing step is to do clause minimization. We don't have anything like that. And one reason for that, like how would you even compare what is a good constraint or a bad constraint? For clauses, this is kind of easy, and in some sense, the smaller the clause is, the better, more or less. There are other measures of small, like literal block distance, but pretty much like it's a one-dimensional thing. But if I have a strong pseudo-Boolean constraints with many variables, or a weaker constraint with smaller coefficients, or like you have several dimensions in pseudo-Boolean constraints. So it's not at all obvious. And we also don't understand in theory how to compare different conflict analysis methods. How to make decisions, how to bump variables for a sort of VSIT score. All of these things, we've just borrowed them from CDCL solving. Maybe we should try to adapt them to pseudo-Boolean setting. Phase saving, this fact that when we decide on a variable, we set it to the last propagated value. Is that the obvious thing to do for pseudo-Boolean solving also? Could we do something else? SAT solvers have experimented with more sophisticated versions of phase saving, also different modes, sort of SAT solvers can run in SAT mode, where you optimize performance for unsatisfiable instances, and unsat mode, where you try to optimize for unsat, and then the solver switches back and forth because it doesn't know. We don't have anything like this for pseudo-Boolean solving. Integrating local search would be great. There's some work on some of these questions, but it's mostly unexplored territory. More efficient unit propagation. We'll hear some about this this week, the latest news, but there's still left work there. Even detecting whether you actually have a unique implication point constraint or an assertive constraint on what this even means during conflict analysis is a challenge. Of course, it wouldn't be me if I didn't also mention that proof logging is a challenge, but we won't talk about this today. So certifying that your algorithm does the right thing. Wrapping up, some references for some of this material is in the handbook of satisfiability. But if you want to read about the conflict analysis, you probably cannot read the MaxSAT and pseudo-Boolean chapters. You have to look at the theory chapter 7. I think that's the only reference I know of for an explanation of pseudo-Boolean conflict analysis. And for this reason, I guess the kind of things I'm doing now, we're trying to record this, we'll try to put it online, make it available as a resource. I think would be a need for more expository material here. But we also maybe need to understand this better before we can write good exposition. So it's time to wrap up this second tutorial. The pseudo-Boolean framework is expressive, but it's close enough to SAT that you can do a conflict-driven algorithm. In theory, this should be exponentially more powerful. In practice, maybe not so much yet. It's hard to design algorithms. There are implementation challenges. We also don't understand the theory very well. On the other hand, there has been precious little work, and SAT solvers took something like 50+ years to mature. If we just invest a little bit of time in this, then maybe there's lots of low-hanging fruit. And even if there isn't low-hanging fruit, there's lots of fun research to be done. So, I think we should work on this. And this concludes the second lecture. Questions?
Yes, I have one.
Yes.
So you state that some pseudo-Boolean solver use a conflict-driven paradigm. So they transform directly into CNF, they use CDCL, and then they come back to pseudo-Boolean optimization, right?
Yes.
Can we do the opposite? So I have my SAT solver, I try, I see that it performed badly. Okay, I go to pseudo-Boolean optimizations, I use cutting plane that is stronger to the URF new constraints, and then I plug these new constraints to SAT that maybe couldn't have found without.
Yeah, so the problem, so far, no. And I think the problem is, again, that the pseudo-Boolean, so like everything I told you so far, it just degenerates to CDCL if you feed it clauses. Yeah. So before you do that, you'd have to somehow realize that maybe this CNF is a 0-1 interlinear program. Let me rewrite it. Okay. And these are these good rewriting algorithms, sort of realizing that there's a better 0-1 encoding for this, 0-1 ILP encoding. We don't quite know how to do this.
Okay.
More questions?
There's one thing. So I know all this from working on BDDs and encoding of pseudo-Boolean constraints into SAT. Mm-hmm. Okay, so it's a related topic. That it's a particularity of pseudo-Boolean constraints that usually you can change, let's say, the right-hand side constant, mm-hmm. increase it or decrease it inside the range. And this doesn't change the constraint. It's exactly the same. Mm-hmm. Okay, so actually every pseudo-Boolean constraint has an associated range, and any value of the constant can give the same constraint. Mm-hmm. The question would be if this is taken into account. I mean, if the constant is pushed to some of the extremes of the range, if it doesn't matter, I don't know.
I think the short that's an excellent question. I think also these kind of things, like a MIP solver would try to figure out these kind of things. The pseudo-Boolean solvers don't. I think in our normalized setting, if we can get a larger degree of falsity, sort of intuitively, you would always take it. But we're not detecting this. And like maybe there are cheap ways of detecting that I can increase my degree of falsity. I don't know that this is being done. I think it would probably help to do it. It's not being done.
Okay.
Okay. Thank you so much. I think we're breaking for lunch now.